So let's look at the following situation. Let's suppose we have a 7-meter long ladder that stands against a frictionless wall a distance of 5 meters above the ground, which has friction. So the wall against which our ladder is resting is frictionless, but the ground has friction. Assuming the ladder has a uniform mass of 10 kilograms, we want to find the force of friction that's acting on the ladder that's actually holding that ladder up. So we're making the assumption that the ladder is in static equilibrium. It's not rotating and it's not translating along any axis. So we have the following ladder, which has a uniform mass of 10 kilograms, a distance of 7 meters. The distance from the ground to where the ladder is resting is 5 meters. This distance is unknown, which we'll find in just a moment. Now, let's see all the forces that's acting on our ladder. We have 3 forces acting on the ladder. We have the red force, which is created by the wall and acts on the ladder and points along the x-axis. We have the purple force, which is the force of gravity that acts on the ladder at the center of mass, exactly in the middle of this distance. And we have the blue force, which acts at some angle with respect to the x-axis, which we don't know. And this blue force is the force of friction that's created by the ground and acts on the ladder. Now notice our blue force is a 2-dimensional force, and that means this blue force has a y component, a force that points along the y-axis, and an x component, a force that points along the x-axis. So we're first going to find the x component force and the y component force of the blue force, and then we're going to use those 2 components to find the actual value of this blue force. So let's begin by recalling that the ladder, our object, is in static equilibrium. And that basically means that the net force acting on our ladder along the x-axis is 0, and the net force acting on our ladder along the y-axis is also 0. So we have 2 forces acting on the ladder that point along the x-axis. So we choose going in this direction along the x-axis to be positive, and in this direction to be negative. So that means our blue force, x vector, x component, is positive, and our red force, due to the wall acting on the ladder, is negative. So we have fx minus f is equal to 0, and for the y component, our y component going up is positive, and our purple force going down is negative. So we have the force of friction, y component, minus the gravitational pull on the ladder, the purple force, is equal to 0. So notice that if we take this equation and we arrange the equation, we bring the purple force to the right side, we see that the force of friction acting along the y component is equal to m times g, where m is the mass of the ladder. So 10 kilograms multiplied by 9.8 meters per second squared, and we get a quantity of 98 newtons. So this force of friction has a y component force of 98 newtons. Now let's try to find our x component force of the force of friction. And to do this, we have to use torque. So we basically choose axis of rotation to be at the point where the ladder touches our floor, our ground, which has friction. So we choose this point to be our axis of rotation. Now let's find what this distance is. So we know that this distance, our hypotenuse of the right triangle, is 7. We know the height of the right triangle is 5. And we want to calculate what the base of our right triangle is. So we simply use our Pythagorean theorem, and we get x is equal to the square root of the difference of the squares. So 7 squared is 49. So 49 minus 25, we take the square root and we get approximately 4.9 meters is the distance of this base. So x, which is the base, is 4.9 meters. So now let's take our torque equation. The sum of the torques acting on the object is equal to, we choose this torque going this way in the clockwise direction to be positive, and this torque going in the counterclockwise direction to be negative. So torque created by the force of gravity, the purple force, minus the torque created by this red force is equal to 0. We take this torque and bring it to the right side. We get the following result. And now recall that torque is simply equal to the force acting on the object multiplied by the lever arm. The distance, the perpendicular distance from the axis of rotation to where the force is acting. So notice the perpendicular distance from our axis of rotation is simply exactly half of the base. So it's x divided by 2 because the force of gravity acts at the center of mass of our uniform mass ladder. So we have the gravitational force is mg multiplied by the lever arm, x divided by 2, and this is simply the red force multiplied by h, the distance of the lever arm for this force. So this force points along the x-axis, and this distance, which is perpendicular to this force, is simply 5 meters, which is h, the height. So now we want to calculate what F is. Why do we want to calculate what F is? Well, because we want to use this equation, which we label as I, to solve for Fx, the x component of the force of friction. So we solve for F and we get F is equal to mgx divided by 2h. So 10 kilograms times 9.8 times 4.9 divided by 2 times 5 meters. And we get approximately 49 newtons. And now we use equation I and we rearrange. We see that Fx, our force of friction along the x-axis, is equal to our red force F, which we found to be 48 newtons. So that means now we can use the two component forces to actually calculate what the quantity of our force of friction is, the blue force. So we have our force of friction is equal to the square root of the sum of our two components. So we have Fx squared plus Fy squared. Take the square root of the squares of the sums. We get 98 squared plus 48 squared. We take the square root of the sum and we get approximately 109 newtons. So the force of friction that's created by the ground on the ladder, that's holding the ladder up, that's creating static equilibrium, has a quantity of 109 newtons.